All right, welcome back to ArmanisMath. Today we're going to focus on graphs of trigonometric functions, graphs of trig functions. The warm-up is going to be here for a few seconds, but please take your time. I'd probably say a couple minutes should suffice for this warm-up, and then I'm going to give you the answers in a few seconds. Here are the answers. The focus today is going to be the tangent, cotangent, secant, and cosecant graphs. The objective for today, I will be able to recognize and graph trigonometric functions. And a real-life application of trig functions is basically trig functions can be used to roof a house or even designing a satellite system. A lot of applications for trig functions. If you think of another example, share that with us in the chat or the live stream comments, and enjoy the ride today. Okay, so if we are focused on the tangent and the cotangent, let's talk a little bit about them. The tangent function and the cotangent can be graphed on a coordinate plane. We looked at the similar ones, which were the sine and cosine, if you guys remember. And the tangent function is undefined when theta equals pi over 2 or 90 plus pi n's, any multiples of pi's after that. For example, 90 plus a pi, 90 plus 2 pi's, 90 plus negative 2 pi's, 90 minus 3 pi's, etc. N could be positive and negative. The cotangent function is undefined when theta is pi n. Pi n means at the pi exactly at 180, right? So just keep that in mind. These values are excluded from the domain and are represented by vertical asymptotes on the graph. So the graphs will not intersect these lines since it's an asymptote. Because the tangent and cotangent value have no maximum or minimum values, the amplitude is undefined. This is something unique about the tangent and cotangent. They have no maximum, like the sine and cosine, they have a maximum of 1. But the cotangent and the tangent don't have actually a maximum of that. Okay? The graph of tangent and cotangent, to graph them, we're going to let the x be the angles and in a standard position. So here's a kind of a synopsis on what should you expect when you graph the tangent and cotangent. On the left side is the tangent, and if you could look closely here, I know that tangent is undefined at pi over 2. So when you take notes, please remember that there's, if you guys remember the unit circle, so I'd probably have a unit circle here right next to me. And then look into where the, can somebody tell me what's the definition of tangent? What's the definition of tangent? Adjacent is opposite over adjacent. So if, obviously, if you have an adjacent of 0, or let's say it's, in this case, we're going to deal with sine and cosine. So in terms of sine and cosine, what would tangent be? Sine and cosine. Because that's going to be the key for you to finding the asymptotes. What is tangent in terms of sine and cosine? Come on, champions. What is tangent in terms of sine and cosine? So tangent, you just told me it's opposite over adjacent. So opposite is y over x, or again sine over cosine. So you want to avoid where cosine is 0. Here we go. You want to avoid where cosine is 0 because it's undefined. And that's the value that you have exactly a vertical asymptote. That's what they're trying to point out here. So in this graph, for example, let me ask you a question. What is cosine 90? Can somebody tell me what's cosine 90? Cosine 90. I would look again. Just remember the cosine 90? Yep, it is 0, and because 0 at the bottom actually gives you undefined value. That's why you have in front of you here the pi over 2 at 90 and the multiples, and I should say 90 and then pi ends, every pi from the 90. So what is 90 plus 180? Does anybody know? 90 plus 180 is how much? Hopefully you have the unit circle. Here we go. At 270 also you have an undefined tangent. And also the multiples of that, right? So 270, and then you're going to go back if you're going to rotate 360 plus 90, etc., etc. The range for the y, for the tangent, as we were told, it goes all the way up to infinity and all the way down to infinity, negative infinity to infinity. The period is also different from the sine and cosine. The period is only 1 pi. So you start and finish the entire wave in 1 pi only. Basically in 180 degrees, you start the wave and you finish the wave for the tangent. And this is why also, because the range is so wide and it's unlimited, and it's like, I mean, sky's the limit here. So the amplitude is also undefined in this case. Conversely, the cotangent is what you see here, and the cotangent is, if you guys remember, it's the reciprocal of tangent, and reciprocal is graphed like that. So basically you are reflecting it. If you could look here, this is basically the reflection, with one minute difference here, that the domain is for when every x's that does not have pi ends. So every pi, basically you can't have that. And why is that? So what's the definition of what is the definition of cotangent? Can somebody tell me what's the definition of cotangent? I'm talking about in terms of sine and cosine. 1 over 10, and I like that, that's fine. Or also sine. How about in terms of sine and cosine? What's the definition of tangent? Here we go. They actually, tangent was sine over cosine. This one is the reciprocal of that, which is cosine over sine. So basically what they're saying, find where is the sine 0, and that's where you're going to have the asymptotes for the cotangent. So when does the sine equal to 0? Does anybody know? On the unit circle, when does the sine equal to 0? Let me ask the question a different way. What is sine 180? What is sine 180? Here we go. And what is sine 0? Here we go. 0 is also that. So sine 0 is 0. Or obviously 360 is also 0, and sine 180 is 0. So any multiples of these guys will give you an asymptote at the, will give you a vertical asymptote at this location. That's why you have, again, the pi n for the asymptotes here. You can't include these values that we just mentioned because these are having a 0 in the bottom denominator, which makes it, again, undefined. The range for the cotangent is from negative infinity to infinity, and again the period is 1 pi only. In 180 this cotangent starts and finishes the cycle, and the amplitude is undefined since you have no limit at either direction, at the top or the bottom. This one says, like the sine and cosine, you can transform the tangent. So we just finished talking about the parent, right? Now the kids are a little bit different. They might be wider, they might be slower, they might be faster, just like the case with the sine and cosine kids and children. And in this case, the period for the kids, so if you have, for example, a tangent graph, which is y equals a tangent bx, where a does not equal to 0, then in this case the period is going to be pi divided by the absolute value of b. Does anybody remember what was the period for sine and cosine? What was the period for the child function for sine and cosine? Does anybody remember that little formula? It shouldn't be that hard. We do a lot of problems on it. Here we go. 2 pi over b. 2 pi over the absolute value of b. In the tangent and cotangent, it's only 1 pi. So don't forget that. The tangent and the cotangent have a period of 1 pi. All right. So you find the period for the child by having the pi divided by the absolute value of b. There's also an asymptote located at x equals pi over 2b plus the pi n over b. If you want to find out the asymptotes once they started to repeat themselves, so they do repeat themselves at pi over 2b plus pi n over b. Here's an example of a tangent that is obviously a child here. This is a child graph of a tangent, and this one goes like this. If you have using f of x as a tangent, x as a guide, graph g of x, which is 1/2 tangent 1/3 x. Identify the period and the x-intercepts and the asymptote. Okay, how do I do that? How do I do that? Well, step number 1 is to identify the period. Does anybody remember what was the period for, what's the formula for the period for this dude here? Does anybody remember? Do you remember? It's pi over, remember it was pi over, right? Not 2 pi. So we're going to have to say, obviously have to identify the b first, and then you're going to say pi divided by that b, which in our case here it's 1/3. So pi divided by 1/3 will do the reciprocal of that. That becomes 3 pi's. So every 3 pi there is a period, meaning I have to finish the whole cycle, the whole wave in 3 pi's. Well, that's unusual because the parent has only 1 pi to finish. That's fine. This is apparently a wider tangent child. Now, to find the x-intercepts, where basically you're touching the x-axis, the first x-intercept occurs at x equals 0 because the period is 3 pi, so the x-intercept occurs every 3 pi. Every 3 pi in either direction, negative or positive. And the third one is to identify the asymptotes. And the asymptotes here, if you guys remember that little formula, if you know that b is 1/3, then the asymptotes occurs at pi over the 2b, with the absolute value of b. And if you did the fraction correctly, you'll end up with pi over 2/3. And obviously that is the reciprocal and becomes 3 pi over 2. So every 3 pi over 2. Well, how much is 3 pi over 2? Does anybody remember? What is 3 pi over 2? In terms of degrees? It's okay. Share your thoughts. Share your thoughts. Here we go. 270. So every 270, for this child, by the way, every 270, so I must start at 270, there's an asymptote, and then every other I should say every 3 pi from there, either direction, negative or positive. So 370 basic plus another 3 pi, that's the second asymptote on the right side, or 370, or 270 I should say, minus 3 pi on the other side. So that's going to be another asymptote. The graph of this would look like that, a little bit wider. You could see it like really stretched if you could look closely, it's pretty stretch here, as if you're compressing it from the top and stretching it. All right. Let's move on to the second example, and this one is transforming tangent. Let me actually move on to another one. I'm going to move on to the graph of the cotangent. Okay, the cotangent has the same thing, so it's y equals a cotangent bx. That's the equation. And what we're trying to do again is know the period, which is pi over b, and the asymptotes located are pi n over b, and b is the integer. Again, you could use either negative or positive. So here's a transformation of the cotangent. I have using cotangent x as a guide, a parent. Use this, find out how to graph this child. G of x is 1/2 cotangent 3x. Identify the period, the x-intercepts, and the asymptotes. So first thing first, I need to identify the period. The period is, once again, pi over b. What is the b here? Well, I'm looking here, right next to me, right next to the x. To the left of the x is the b, or to the left of the angle. So pi divided by b is pi divided by 3. So basically pi over 3, which is, how much is that? How much is pi over 3? I'm just curious. In degrees, how much is pi over 3? Hey, that's it. So every 60 degrees, I have a full length, a full wave of this cotangent. That's a pretty fast child. If the parent itself take a pi to start and finish like 180, this guy takes 1/3. This guy is very fast. Second is to identify the x-intercepts. The x-intercepts, the first one happens at pi over 6, which is exactly pi over 6. That is because, why is it pi over 6? Pi over 6 is 30, by the way. Because the period is pi over 3, and the x-intercepts happens at, occurs at x is pi over 6 plus pi over 3 n's. So every pi over 3 n's, but the first one happens in the middle of that, which is at pi over 6. I did have a comment here saying use Desmos, so we will probably quickly take a look at that, or unless if you guys want to do it also on your own. I would just graph this simple g of x. I would actually put both of them. Put cotangent x and then put also the 1/2 cotangent 3x. Obviously there's a graph here I want to show you, but identify the asymptotes. Because b is 3, the asymptotes occur at pi n divided by 3, or pi divided by 3 and then times n. Pi divided by 3, as in we said it's pi divided by 3, we said it's 60, so basically every 60. So 60 is going to have 1, 120 is going to have 1, and then 60 is going to have 1, and then go back, if you like, to the other direction. That's going to be 0, right? So either directions, but multiples of 60 are going to have asymptotes. So how does the graph of this look like? A little bit skinnier, obviously, because you're going to start and finish pretty fast. This wave is going to start and finish pretty fast, faster than the parent, obviously. It takes 1/3 of the parent to start and finish the wave. Okay, so that is the graph of the cotangent, and I definitely wanted you to be exposed to the secant and cosecant. Okay, so we're gonna move on to the other two, unless if we have questions here. I'm monitoring the chats here at the same time. Okay. Let's move on to this coming one, and this one is going to be, I wanted you to see the secant and cosecant. A little bit different concept here on graphing. I like these kind of unique guys here, pretty unique. So watch for a second the secant, the one on the left here first. We said that the secant defined as what? What's over what gives you secant, by the way? Secant is what over what? Yes, Taylor. Most likely we're going to be recording also another one. Okay. What is the secant again? What's the definition of secant? Hello. Secant is what? You guys are going to help me, right? 1 over cosine is, yep, 1 over cosine. So basically, whenever there is a 0 for the cosine at the bottom, whatever the value that makes cosine 0, that means these values I can really have, right? I can't have that because at these values it's undefined. But guess what? At these values, I'm going to have a vertical asymptote. So now go ahead and tell me what angles give you a cosine of 0. That's basically what we have to find out. What angles give me a cosine of 0? You're going to have a unit circle right next to you, like it's like your best buddy here. At 90 and at 270. And if you look closely at the graph here, at 90 I'm going to have a vertical asymptote. That's the green line here, vertical asymptote. And at 270 I also have a vertical asymptote. So the best thing, here's my secret for secant and cosecant. The best thing to graph them is actually to graph the parent sine and cosine first, and then on top of it will go the other curves. One more time. Let's, for example, I want to graph the secant. Well, you graph the secant is what? Is the reciprocal of cosine. So you're going to graph the cosine. Look at the blue line here, dashed line. I'm going to graph the cosine first. Remember, cosine starts from 1. Goes all the way to 0, -1, 0, and then 1 again. So you graph the cosine first, and on top of it is going to live the secant. And look at the red ones is the secant here. It looks like Christmas colors here. The domain for the secant is going to be everything except, obviously, the ones that you have undefined values for, which happens when the cosine is 0. That's what's easier, to graph the cosine first, and on top of it will go the curves for the secant. The range is also the range is unique for the secant and cosecant. Look exactly what happens to the range. Because it's discontiguous, I should say. There is a gap here. So this red one at the top, and then there's a gap, and then there's a red one at the bottom. So from basically, if you were talking about range, I'm going to start from 1 all the way to infinity at the top. And then I have to leave myself a gap, -1, all the way to the infinity at the bottom. So basically anything from 1 all the way to infinity, or -1 to -infinity. Nothing in between 1 and -1. And what's going to live between 1 and -1 is actually the cosine parent function, not the child. The period for the secant, because it's related to the cosine. Does anybody remember what's the period for cosine? What's the period for cosine? Two pi's. That's exactly what's going on. So because cosine is 2 pi's, the period for secant is also going to be 2 pi. The period for sine is going to be 2 pi, so the cosecant also has a period of 2 pi. That's an easy thing to relate to and associate. Amplitude is undefined again because you could go all the way up or all the way down. There's no limit here. Conversely, the cosecant function, you need to graph the sine first. So look at the blue here. I'm graphing the sine function, which starts from 0, 0, 1, goes to 0, -1, and then goes back to 0. So I'm going to graph the sine first, and on top of it is going to live my cosecant function. And remember, it's 2 pi's, okay? So if you are looking at this graph, you're going to start from here all the way to here to get you to 2 pi with these curves here. See this curve at the top, curve at the bottom. All right, same information with one exception here. The x does not equal to pi or pi n. What is pi again? What is pi in degrees? Okay, and what is the sine of 180? What's sine 180? Hopefully you have your unit circle right next to you. Sine 180 would be sine 180. So think again. Sine 180. Look at the unit circle. Anybody else want to chime in? Sine is sine 180 is, drum roll. Yep, so cosine is -1, sine is 0. So basically, I'm trying to avoid these points. I can't have a sine equals 0 for the cosecant. Otherwise, I'm going to have undefined. However, I'm trying to avoid it because it's not part of my domain. At the same time, it's useful because it tells me there's an asymptote there. So basically, I have an asymptote at these locations here. That's why it's very easy to graph the sine first and then on top of it the cosecant. This one says using f of x as cosine, then graph the secant function. Obviously, the cosine the secant is a reciprocal of cosine. So I have 1/2 secant, 1/2 x. Identify the period. Because secant is 1/2 x, it's a reciprocal of the cosine of 1/2 x with the same period. So I've got myself a b equals 1/2, and in this case pi over b, or 2 pi over 1/2, which is going to give you a 4 pi's here. 4 pi's for this. So basically a little bit wider to start and finish these waves here for the cosine. Asymptotes happen at, because the period is 4 pi, the asymptotes happen at pi over 2 over b. In this case, it's going to happen at pi plus 2 pi, every pi plus 2 pi n's, like 2 pi's, 3 pi's, -2 pi's, -4 pi's for these asymptotes. You could tell here that it takes a long time for it to start and finish its wave because the period here is 4 pi's for this child. Twice as slow as the parent. Maybe this child just takes it through time and doing the work. And lastly is going to be this one here. This is a cosecant graph, which is, again, we're using the sine as a guide. And we are 2 cosecant of x. I'm going to find the period, which is 2 pi over 1 in this case, because whatever next to the x is going to be that b, 2 pi. So almost like the parent, the asymptotes here are going to be at every pi n. And the graph for this guy would be almost like the parent, except one exception, that the length, the height I should say, the starting point is going to be 2 instead of 1 with the regular cosecant. Okay, I know that was too much, but this video is probably going to be helpful. I'm going to do another one, and also the textbook is another resource. And we're going to discuss this also next time when I see you as well. So here is the quiz at the end. I'll give tangent as a guide, graph, negative tan. I do give you the quiz answers. Please don't just give me the answer. Try to avoid giving me just the answer and they work, because that's not work. Just to help you. This one would look like that. And there is also another one. This one is cosecant. It's 1/3. Cosecant 1/3 x. And also they're asking you to identify the period and asymptotes. You need to pause here before you look at the answers, obviously, and try to quiz yourself. But it should look like that. 6 pi's. Wow, that's pretty slow. Child, which is fine. And then asymptotes are x equals 3 pi n's. Every 3 pi happens an asymptote, either directions. All right, champions. Okay, let's see how we're doing here. All right, until I see you guys next time, have a blessed day. Take care of yourselves and stay healthy.